In mathematics, a manifold is a topological space that resembles Euclidean space near each point. More precisely, each point of an n-dimensional manifold has a neighbourhood that is homeomorphic to the Euclidean space of dimension n. One-dimensional manifolds include lines and circles, but not figure eights. Two-dimensional manifolds are also called surfaces. Examples include the plane, the sphere, and the torus, which can all be embedded in three-dimensional real space, but also the Klein bottle and real projective plane, which cannot. Although a manifold resembles Euclidean space near each point, globally it may not. For example, the surface of the sphere is not a Euclidean space, but in a region it can be charted by means of map projections of the region into the Euclidean plane. When a region appears in two neighboring charts, the two representations do not coincide exactly and a transformation is needed to pass from one to the other, called a transition map. The concept of a manifold is central to many parts of geometry and modern mathematical physics because it allows more complicated structures to be described and understood in terms of the relatively well-understood properties of Euclidean space. Manifolds naturally arise as solution sets of systems of equations and as graphs of functions. Manifolds may have additional features. One important class of manifolds is the class of differentiable manifolds. This differentiable structure allows calculus to be done on manifolds. A Riemannian metric on a manifold allows distances and angles to be measured. Symplectic manifolds serve as the phase spaces in the Hamiltonian formalism of classical mechanics, while four-dimensional Lorentzian manifolds model spacetime in general relativity. Motivational examples. Circle after a line. The circle is the simplest example of a topological manifold. Topology ignores bending, so a small piece of a circle is treated exactly the same as a small piece of a line. Consider, for instance, the top part of the unit circle, x2 plus y2 equals 1, where the y-coordinate is positive. Any point of this arc can be uniquely described by its x-coordinate. So, projection onto the first coordinate is a continuous, and invertible, mapping from the upper arc to the open interval. Such functions along with the open regions they map are called charts. Similarly, there are charts for the bottom, left, and right parts of the circle. Together, these parts cover the whole circle and the four charts form an atlas for the circle. The top and right charts overlap. Their intersection lies in the quarter of the circle where both the x and the y coordinates are positive. The two charts chi-top and chi-right each map this part into the interval. Thus a function t from to itself can be constructed, which first uses the inverse of the top chart to reach the circle and then follows the right chart back to the interval. Let a be any number in, then. Such a function is called a transition map. The top, bottom, left, and right charts show that the circle is a manifold, but they do not form the only possible atlas. Charts need not be geometric projections, and the number of charts is a matter of some choice. Consider the charts, and here S is the slope of the line through the point at coordinates and the fixed pivot point, T follows similarly, but with pivot point. The inverse mapping from S to as given by it can easily be confirmed that x2 plus y2 equals 1 for all values of the slope S. These two charts provide a second atlas for the circle, with each chart emits a single point, either for S or for T. So neither chart alone is sufficient to cover the whole circle. It can be proved that it is not possible to cover the full circle with a single chart. For example, although it is possible to construct a circle from a single line interval by overlapping and gluing the ends, this does not produce a chart. A portion of the circle will be mapped to both ends at once, losing invertibility. An rich circle viewed using calculus, the circle transition function t is simply a function between open intervals. which gives a meaning to the statement that T is differentiable. The transition map T, and all the others, are differentiable on. Therefore, with this atlas the circle is a differentiable manifold. It is also smooth and analytic because the transmission functions have these properties as well. Other circle properties allow it to meet the requirements of more specialized types of manifold. For example, the circle has a notion of distance between 2 points, the arc length between the points, hence it is a Riemannian manifold. Sphere. The sphere is an example of a manifold of dimension 2. The unit sphere of implicit equation x2 plus y2 plus z2 1 equals 0 may be covered by an atlas of 6 charts. The plane z equals 0 divides the sphere into 2 half-spheres, which may both be mapped on the disk x2 plus y2 less than 1 by the projection on the xy plane of coordinates. This provides 2 charts. The 4 other charts are provided by a similar construction with the 2 other coordinate planes. As for the circle, one may define one chart that covers the whole sphere excluding one point. Thus 2 charts are sufficient, but the sphere cannot be covered by a single chart. This example is historically significant, as it has motivated the terminology. It became apparent that the whole surface of the Earth cannot have a plane representation consisting of a single map, and therefore one needs atlases for covering the whole Earth's surface. Other curves manifolds need not be connected. An example is a pair of separate circles. Manifolds need not be closed, thus a lined segment without its endpoints is a manifold, and they are never countable, unless the dimension of the manifold is 0. Putting these freedoms together, other examples of manifolds are a parabola, a hyperbola, and the locus of points on a cubic curve y2 equals x3 minus x. However, excluded are examples like 2 touching circles that share a point to form a figure 8. At the shared point a satisfactory chart cannot be created. Even with the bending allowed by topology, the vicinity of the shared point looks like a plus, not a line. A plus is not homeomorphic to a closed interval, since deleting the center point from the plus gives a space with 4 components, whereas deleting a point from a closed interval gives a space with at most 2 pieces. Topological operations always preserve the number of pieces. History. The study of manifolds combines many important areas of mathematics. It generalizes concepts such as curves and surfaces as well as ideas from linear algebra and topology. Early development. Before the modern concept of a manifold, there were several important results. Non-Euclidean geometry considers spaces where Euclid's parallel postulate fails. Zachary first studied them in 1733. Lobachevsky, Bollier, and Riemann developed them 100 years later. Their research uncovered 2 types of spaces whose geometric structures differ from that of classical Euclidean space. These gave rise to hyperbolic geometry and elliptic geometry. In the modern theory of manifolds, these notions correspond to Riemannian manifolds with constant negative and positive curvature, respectively. Carl Friedrich Gauss may have been the first to consider abstract spaces as mathematical objects in their own right. His theorem or egregium gives a method for computing the curvature of a surface without considering the ambient space in which the surface lies. Such a surface would, in modern terminology, be called a manifold, and in modern terms, the theorem proved that the curvature of the surface is an intrinsic property. Manifold theory has come to focus exclusively on these intrinsic properties, while largely ignoring the extrinsic properties of the ambient space. Another, more topological example of an intrinsic property of a manifold is its Euler characteristic. Leonhard Euler showed that for a convex polytope in the 3-dimensional Euclidean space with V vertices, E edges, and F faces, the same formula will hold if we project the vertices and edges of the polytope onto a sphere, creating a topological map with V vertices, E edges, and F faces, and in fact, will remain true for any spherical map, even if it does not arise from any convex polytope. Thus 2 is a topological invariant of the sphere, called its Euler characteristic. On the other hand, a torus can be sliced open by its parallel and meridian circles, creating a map with V equals 1 vertex, E equals 2 edges, and F equals 1 face. Thus the Euler characteristic of the torus is 1 minus 2 plus 1 equals 0. The Euler characteristic of other surfaces is a useful topological invariant, which can be extended to higher dimensions using Betti numbers. In the mid-19th century, the Gauss-Bonnet theorem linked the Euler characteristic to the Gaussian curvature. Synthesis investigations of Niels Henrik Abel and Carl Gustav Jacobi on inversion of elliptic integrals in the first half of 19th century led them to consider special types of complex manifolds, now known as Jacobians. Bernhard Riemann further contributed to the theory, clarifying the geometric meaning of the process of analytic continuation of functions of complex variables. Another important source of manifolds in 19th-century mathematics was analytical mechanics, as developed by Siméon Poisson, Jacobi, and William Rowan Hamilton. The possible states of the mechanical system are thought to be points of an abstract space, phase space in Lagrangian and Hamiltonian formalisms of classical mechanics. This space is, in fact, a high-dimensional manifold, whose dimension corresponds to the degrees of freedom of the system and where the points are specified by their generalized coordinates. For an unconstrained movement of free particles, the manifold is equivalent to the Euclidean space, but various conservation laws constrain it to more complicated formations, e.g., Liouville-Torrey. The theory of a rotating solid body, developed in the 18th century by Leonhard Euler and Joseph Louis Lagrange, gives another example where the manifold is non-trivial. Geometrical and topological aspects of classical mechanics were emphasized by Henri Poincaré, one of the founders of topology. Riemann was the first one to do extensive work generalizing the idea of a surface to higher dimensions. The name manifold comes from Riemann's original German term, mannigfaltigkeit, which William Kingdon Clifford translated as manifoldness. In his Göttingen inaugural lecture, Riemann described the set of all possible values of a variable with certain constraints as a mannigfaltigkeit, because the variable can have many values. He distinguishes between Stetiger mannigfaltigkeit and discrete mannigfaltigkeit, depending on whether the value changes continuously or not. As continuous examples, Riemann refers to not only colors and the locations of objects in space, but also the possible shapes of a spatial figure. Using induction, Riemann constructs an n-var-cosgedente mannigfaltigkeit as a continuous stack of dimensional manifoldnesses. Riemann's intuitive notion of a mannigfaltigkeit evolved into what is today formalized as a manifold. Riemannian manifolds and Riemann surfaces are named after Riemann. Poincaré's definition in his very influential paper, Analysis Citis. Henri Poincaré gave a definition of a manifold which served as a precursor to the modern concept of a manifold. In the first section of Analysis Citis, Poincaré defines a manifold as the level set of a continuously differentiable function between Euclidean spaces that satisfies the non-degeneracy hypothesis of the implicit function theorem. In the third section, he begins by remarking that the graph of a continuously differentiable function is a manifold in the latter sense. He then proposes a new, more general, definition of manifold based on a chain of manifolds. Poincaré's notion of a chain of manifolds is a precursor to the modern notion of atlas. In particular, he considers two manifolds defined respectively as graphs of functions, and if these manifolds overlap, then he requires that the coordinates depend continuously differentiably on the coordinates and vice versa. In this way he introduces a precursor to the notion of a chart and of a transition map. Note that it is implicit in Analysis Citis that a manifold obtained as a chain is a subset of Euclidean space. For example, the unit circle in the plane can be thought of as the graph of the function, or else the function in a neighborhood of every point except the points, and in a neighborhood of those points. It can be thought of as the graph of respectively, and. The reason the circle can be represented by a graph in the neighborhood of every point is because the left-hand side of its defining equation has non-zero gradient at every point of the circle. By the implicit function theorem, every submanifold of Euclidean space is locally the graph of a function. Hermann Weyl gave an intrinsic definition for differentiable manifolds in his lecture course on Riemann surfaces in 1911–1912, opening the road to the general concept of a topological space that followed shortly. During the 1930s, Hassler, Whitney and others clarified the foundational aspects of the subject, and thus intuitions dating back to the latter half of the 19th century became precise, and developed through differential geometry and Lie group theory. Notably, the Whitney embedding theorem showed that the intrinsic definition in terms of charts was equivalent to Poincaré's definition in terms of subsets of Euclidean space. Topology of manifolds highlights two-dimensional manifolds, also known as a 2D surfaces embedded in our common 3D space, were considered by Riemann under the guise of Riemann surfaces, and rigorously classified in the beginning of the 20th century by Paul Heegaard and Max Dehn. Henri Poincaré pioneered the study of three-dimensional manifolds and raised a fundamental question about them, today known as the Poincaré conjecture. After nearly a century of effort by many mathematicians, starting with Poincaré himself, the consensus among experts is that Grigori Perelman has proved the Poincaré conjecture. William Thurston's geometrization program, formulated in the 1970s, provided a far-reaching extension of the Poincaré conjecture to the general three-dimensional manifolds. Four-dimensional manifolds were brought to the forefront of mathematical research in the 1980s by Michael Friedman, and in a different setting, by Simon Donaldson, who was motivated by the then recent progress in theoretical physics, where they serve as a substitute for ordinary, flat, space-time. Andrei Markov Jr. showed in 1960 that no algorithm exists for classifying four-dimensional manifolds. Important work on higher-dimensional manifolds, including analogues of the Poincaré conjecture, had been done earlier by René Thom, John Milnor, Stephen Smale and Sergei Novikov. One of the most pervasive and flexible techniques underlying much work on the topology of manifolds is Morse theory. Mathematical definition. Informally, a manifold is a space that is modeled on Euclidean space. There are many different kinds of manifolds and generalizations. In geometry and topology, all manifolds are topological manifolds, possibly with additional structure, most often a differentiable structure. In terms of constructing manifolds via patching, a manifold has an additional structure if the transition maps between different patches satisfy axioms beyond discontinuity. For instance, differentiable manifolds have homeomorphisms on overlapping neighborhoods diffeomorphic with each other, so that the manifold has a well-defined set of functions which are differentiable in each neighborhood, and so differentiable on the manifold as a whole. Formally, a topological manifold is a second countable Hausdorff space that is locally homeomorphic to Euclidean space. Second countable and Hausdorff are point-set conditions. Second countable excludes spaces which are in some sense too large, such as the long line, while Hausdorff excludes spaces such as the line with two origins. Locally homeomorphic to Euclidean space means that every point has a neighborhood homeomorphic to an open Euclidean n-ball. Generally, manifolds are taken to have a fixed dimension, and such a space is called an n-manifold. However, some authors admit manifolds where different points can have different dimensions. If a manifold has a fixed dimension, it is called a pure manifold. For example, the sphere has a constant dimension of 2 and is therefore a pure manifold, whereas the disjoint union of a sphere and a line in 3-dimensional space is not a pure manifold. Since dimension is a local invariant, each connected component has a fixed dimension. Scheme: theoretically, a manifold is a locally ringed space whose structure or sheaf is locally isomorphic to the sheaf of continuous functions on Euclidean space. This definition is mostly used when discussing analytic manifolds in algebraic geometry. This omits the point set axioms, allowing higher cardinalities and non-Hausdorff manifolds, and it omits finite dimension, allowing structures such as Hilbert manifolds to be modeled on Hilbert spaces, Banach manifolds to be modeled on Banach spaces, and Frechet manifolds to be modeled on Frechet spaces. Usually one relaxes one or the other condition. Manifolds with the point set axioms are studied in general topology, while infinite-dimensional manifolds are studied in functional analysis.